Hi everyone, I'm Mr. Fullerton, and today I'd like to talk to you about some of the basics of waves. Our objectives are going to be to define a pulse and talk about the behavior of a pulse at a boundary. We'll also talk about the characteristics of transverse and longitudinal waves and explain the characteristics of electromagnetic and mechanical waves. So, a pulse is a single disturbance which carries energy through a medium or through space. Key point here is it carries energy, not mass, not matter. Energy is what's carried by a pulse. Imagine you and your friend are holding opposite ends of a slinky. If you quickly move your arm up and down, a single pulse will travel down the length of the slinky. The energy of your pulse is what's traveling. The mass, the matter of the slinky, for the most part, stays in the same position compared to the direction of travel. Yeah, it moves up and down a little bit, but it's really the energy that's doing most of the traveling. Now, if you have several pulses at regular intervals, you've created a wave. And again, a wave carries energy. It's a repeated disturbance. The mass of the slinky doesn't really move from one end all the way to the other. It's the energy that is moving as you create a wave by repeated pulses you would apply to the slinky. Mechanical waves require a medium or some substance to travel through. Things like sound or water or seismic waves, they all travel through a medium. Sound travels through the air or water or wood. Water waves travel through water. Seismic waves travel through the earth. Electromagnetic or EM waves, on the other hand, they don't require a medium. They can travel through a vacuum. They can travel through space. Things like light and X-rays and microwaves all can travel through space without a medium. Sound can't travel through space. Now, we could also look at waves based on the direction the particles or the pieces of the wave vibrate compared to the direction of the wave velocity. A longitudinal wave is a wave in which the particles of the wave vibrate in the same direction that the wave travels. So if the wave is traveling across your screen, the particles or pieces of that wave vibrate in that same direction. Things like sound. If you think of sound in air, the sound that's coming from me to you, from the speaker or the computer to you, is vibrating air molecules moving closer and closer. Or seismic P waves. Transverse waves, on the other hand, are waves in which the particles of the wave vibrate perpendicular to the direction of the wave's velocity. So if the wave is traveling this way, the transverse wave has particles vibrating up and down along that wave. And that's probably what you're more familiar with. A slinky, as an example, can make either type of wave. A transverse wave from a slinky, you create a pulse this way, the wave travels that direction. That's transverse. On the other hand, if you compress one end of the slinky and let it go, you will see that compression travel along the slinky. That would be a longitudinal wave. So, sample question 1. Which type of wave requires a material medium through which to travel? Sound, television, radio, or X-ray? Well, sound is the mechanical wave. It requires a medium to travel through. So that's going to be our answer. 1, sound. Another question, the diagram here represents a transverse wave traveling to the right through a medium. Point A represents a particle of the medium. In which direction will particle A move in the next instant of time? Well, if you look at A down here on the wave, A doesn't move with the direction of the velocity. It only moves up and down. So our answer is going to have to be either up or down. Now, as that wave itself travels to the right, A can't move horizontally, so A is going to have to move down to follow along the wave. The other way you can look at this is if you see the velocity of the wave is moving to the right, pretend the particle is moving left along the wave, and you would see that it's going to move down in its next instant of time. As a transverse wave travels through a medium, the individual particles of the medium move, and our choices are perpendicular to the direction of wave travel, parallel to the direction of wave travel, in circles, and in ellipses. Well, if it's a transverse wave, the individual particles of the medium move perpendicular to the direction of wave travel, number 1. That's the definition of a transverse wave. A ringing bell is located in a chamber. When the air is removed from the chamber, why can the bell be seen vibrating, but it can't be heard? Well, here we've got to take a look and realize that light, that allows us to see the bell can travel through a vacuum. It's an electromagnetic wave. Sound, however, is a mechanical wave. It needs a medium through which to travel. So in order for the sound to travel through there, it has to have air. When you pull all the air out of the vacuum chamber, you don't have any medium through which the sound can travel. So the correct answer here is 1. Light waves can travel through a vacuum because they're electromagnetic waves, but sound waves cannot.